take all the heat that goes in and do an equivalent amount of work. There always has to be something that dumps off to here. All right, that's why perpetual motion is impossible. Because you've always got to dump something into the cold. You can never get it 100% efficient. All right. Okay, so in terms of the new chapter, I'm going to want you to know, and I haven't actually officially stated, I'm going to want you to know the second law of thermodynamics, but there's about 10 different ways it gets stated, and so I'm going to give you a few of them. Right, so that's one of the easiest ones to remember. No engine can be 100% efficient. There's a little codicil, unless T sub Z and T sub C equals 0. And then the third law, as you already remember. Let's see that. Can't reach it. You can never get to that. So this is why you probably remember a little early in the course, one student had brought up that there was something that said that you could get perpetual motion. The second law actually comes out of something called the Carnot cycle, and I debated about teaching the Carnot cycle, and you're probably really glad I decided not to, simply because to make it work, I do need a lot of calculus, but the thing that I want to get in your heads, you'll understand it just sketching. We're not going to drive. I want you to understand the basic idea. What Sadi Carnot did, this is a young French physicist who died at the age of 30, so you've got to hurry up if you want to get famous apparently and all that. So what he did is he imagined the most efficient heat engine he could, which he said, I have an isotherm, followed by an adiabat, followed by another isotherm, followed by another adiabat. So it's, you guys just listen, don't write unless you really want this written down, because you're not going to be tested. I just want you to have the idea of it. So it's got 4 strokes. Basically, we're going to run it this way, and because he chose adiabats and isotherms, that means what makes this good is that there's no heat flow along the adiabats, right? Q is 0. On the isotherm, then this means this is my QH, this is my QC, so I have a really clean thing where it's not, I don't have to add up other pieces. There's only one QH, there's only one QC. And it turns out there's a mathematical relationship that ties adiabats together, and when you put those two pieces of information all together, that's where this equation comes from. That's why this is my limiting efficiency. That says this is if you have an ideal engine where nothing is lost at all. Then you have an efficiency that's less than 100. In other words, if there's no friction, there's no anything else interfering with this cycle, this is what you get to. And you can easily prove that there is nothing more efficient than this engine, because if there were, then it could drive this engine and you would get below absolute 0 and you could get 115% efficient, which all makes no sense. So the basic idea I'm trying to sell here is the idea that he came up with the perfect engine called the Carnot cycle. I'm going to write this in case you, right? And proved that it's not 100% efficient. So your Carnot cycle isn't 100% efficient, and it's the best that there even is theoretically, not in real life, the best theoretically. So this is like when we were doing sliding things on the floor at the beginning of the semester, and we were saying, assume no friction, assume no this, all our assumptions in place. That's all the assumptions in place. This is as perfect as it gets, and it's not perfect. So that's how powerful this second law is. Which basically means that at some point, the universe, all the stars have burned whatever they can burn, and heat is everywhere in the universe, and we are basically all one temperature, and when that happens, it's all over. And so it's called the heat death, not the cold death. The universe does not cool off. It actually ends up, on average, hot. Right now, does anybody, out of curiosity, how you read news, what's the current background temperature of the universe? Anybody know? 3 Kelvin. All right, so pretty cold, getting warmer. So when we say warm, it's not going to be hot enough to toast marshmallows, all right? But it's going to be warmer than 0. And when that happens, it's over. I don't know how long you're planning to live. I will definitely be gone. Just for example, the Earth has probably about 5 billion, the Sun has about 5 billion more years before it cools off. And there's other stars that can form. So it's going to be billions and billions of years in the future. All right? So, but the thing is, it also means that the universe is not infinite. It's going to wind down. I don't mean in size, I mean in terms of how long it lasts. It's going to wind down. All right, so all that backing away. Any questions then on the basic things that we've got? We had the 2 chapters. We focused really hard on the first law. We have focused somewhat on the second law. So those 2, we expect some problems on the test. I told you about 2/3 I expect from chapter 12, and about 1/3 to come from chapter 13. The 0th law and the 4th law, we don't have any actual math we can do with them, but I would say it's probably a good idea to be able to write all 4 laws. 0, 1, 2, 3. So anybody got any questions about this? All right, because in your book or whatever, he puts them in slightly different order. Now, I know from experience that a lot of you aren't reading your textbooks, but for those of you who are, on page 486 there isn't a typo, and by now you should recognize it. But in the very first example on the top of the page, they say let Boltzmann's constant equal 1.38 times 10 to the 23rd. It should be 10 to the minus 23, not 10 to the 23rd. That would really throw interesting wrenches in. So, but you know that, right? You know that 1.38 times 10 to the negative 23 because you've used it so much. But it is a typo in the text. I noticed as I was going through. All right. So U, W, Q. These are the path things. W and Q definitely depend on their path. We have paths for which there's delta U, but it does not depend on the path. All right. Then P, V, and T, state variables. So ideal gas law, got to know. And coming along, although I'll give them to you, if you don't know how to use these, you're going to be screwed. All right. So when is this appropriate? When there's a change in temperature. So never for a phase change. This is only when there's temperature changes. And this is what we use for phase changes. What's not always stated, but I want to make clear. We have 2 heats that we have here. One's what we call heat of fusion. One's what we call a heat of vaporization or condensation. The L that's associated with freezing ice and the L that's associated with melting ice is the same L. The L that's associated with boiling water to steam and the L that's associated with steam condensing back to water is the same L. All right? And how many states of matter are there?
4.
There's probably around 20, 30. All right? And you've never heard of them. All right? Because they're really esoteric and weird. So don't get married to the fact that you've only been taught 3, or some of you recognize the 4th one because I mentioned, which is what? Plasma. And stars are basically plasmas. But guys, it turns out if you cool like iron down, it goes through several phase changes into different forms and shapes when you get near the absolute 0. And most metals do. So a lot of the stuff that goes with superconductivity and other kinds of things that you've heard about are associated with phase changes. So don't get married to the idea that there's a particular number. I suspect there's phase changes we haven't figured out yet. All a phase change means is there's a state that requires some input of heat or output of heat to change that state to something else. And it happens in all kinds of ways. Our most common ones that we encounter in everyday life are, of course, the 3 solid, liquid, gas. And those are the ones we'll concentrate on here. We're not going to do plasma. Well, I'll maybe mention again next semester once we do electricity and magnetism. But, so we'll stay with solid, liquid, and gas. We take liquid and gas and we lump them into one thing called fluids. But be sure you pay attention to when equations pertain only to a gas, P equals nRT, and when they apply to anything, Q equals MC delta T. All right? And I'll try to make sure that's a little clearer. I have set up the Chapter 13 homework. I say there's only 3 questions on it, but one of them is this thing I basically outlined, and it's going to take you a while to sort through it. Right, so take a look at it. What I'm going to do is I'll have a practice test for you on Monday, and I'll give you, I think most of you have sort of an idea about some of the problems that are going to show in there, but I'll still have the practice. And then what I will also do is try to give you as many equations as we need on a lot of this, because like I say, there's almost an infinite number of equations rattling around. Are there any questions you have specifically about what you need to do next or how you study on this material? Any other questions on any part of any of the homework?
If we do have problems, we can ask them.
How's that?
If we do have problems, we can ask them.
Yes, absolutely. And so you know what we're going to do is I'm going to give you the practice test on Monday, and I'm going to cover a little bit more material out of this to make sure we're good, and then I'll go over the entire practice test on Wednesday, so make sure you all have the right answers to study with Thanksgiving. Well, it's Thanksgiving, you're giving thanks that there's a test coming on Monday after.